of inner product space. That is, inner product space is a vector space with a function. We call it the inner product. The function needs satisfy four property like that. Then we have a three property. The first one is inequality, Cauchy-Schwarz inequality. The second one is a triangle inequality, and there's the Pythagorean theorem concerning the orthogonal vector U and V with equality like that one. And after that, we begin with the notion of orthogonal projection. First, that is the orthogonal projection of vector U onto a non-zero vector V. It is given by formula like that, or by geometry. You can look something like that one. I think that the geometry will be just much familiar to you. In case the vector V, the non-zero vector V, is a unit vector, means it has the norm 1. Then the formula is much simpler like that one. I put it in the red box like. And we have one property, that is the distance from U, to its orthogonal projection on V is always less than the distance from U to any other vector lying on the line containing the vector V. Or by formula, you can see it here. Or I prefer to look at the geometry like that. Next, we study the notion of orthogonal and autonoman set. A set of vector S, V1, V2, Vn inside inner product space V will be called orthogonal set if we have inner product of Vi and Vj equal 0 for any I different from j. And if more than that, we require that on the vector V has the length 1, then we have the name autonoman set. Now in Vietnamese, the first one has name trực giao and the second one has name trực chuẩn. And if more than that, S is a basis at the same time, then we have the name of orthogonal basis and autonoman basis, cơ sở trực giao và cơ sở trực chuẩn. That is two different name for a basis. One of very useful property of orthogonal set, that is if S is orthogonal set and on the vector inside S is non-zero, then S must be linearly independent. We can use that property to verify if some set is a basis or not by the observation here. In case we know that V is of the dimension n, then the S consists of n vector, n orthogonal non-zero vector must be a basis for space V. That is observation, we say it here. And one of advantages of an autonomous basis, that is, if you are given an autonomous basis in an inner product space V, then then the coordinate column of any vector W inside V can be given like that. I put it in the red box here. The first coordinate is here, the second coordinate is here, the last coordinate is here. Very easy to find it. Just only to take the inner product of the vector W and the vector inside the basis. Or if you write it in the form of a linear combination, you have that one. But I prefer the form in the column like that. Then I define the orthogonal projection of a vector V onto any subspace of W. I said that previously we defined already the orthogonal projection of a vector U onto a non-zero vector V. It is here. And we have a very important property, that is U minus projection of U on V is always orthogonal to V. That is very important property. And what is U minus projection of U on V? That is vector going from here to Z. It is always orthogonal to the vector V, and V is. And we are going to use that property to define what is the orthogonal projection of vector V onto a subspace W. Now assume that W is a subspace of V. Then the projection of V on W is a vector. It is a vector denoted by that, and that vector must lies in the subspace W, and it satisfies that property. So you see, that property is exactly the same like here. So that is what we define for the projection of a vector onto a subspace. And it has one important property, that is the distance from V to its orthogonal projection is less than the distance from V to any other vector W inside the space W here. So that is a notion of orthogonal projection of a vector V onto W. After that, we study the Gram-Schmidt autonomization process. It is the most complicated formula for you in the whole course on linear algebra. The Gram-Schmidt autonomization process is, suppose that you are given any basis B in an inner product space V, then that process will help you to construct first an orthogonal basis B prime, and then you can get an orthogonal basis B double prime. And the only way you can remember, that is you do as many as possible the exercise on that. So you need to remember the formula here. I cannot help you with that. And that slide will show you an example, and that example may help you to imagine the geometry of the Gram-Schmidt process. I explained to you that during the lecture class already. Then we continue with the mass models and least square analysis. First, we define the notion of orthogonal subspaces. Suppose that we are given two different subspaces W1, W2 of the same inner product space V. We say that W1 and W2 are orthogonal to each other if we have the inner product of V1, V2 equals 0 for any V1 inside W1 and any V2 inside W2. You can find example from the geometry in the high school by imagine. You can take a plane and a line orthogonal to each other, and then you can imagine anything is here. After that, we define the notion of orthogonal complement of W. Suppose that you are given W to be a subspace of an inner product space V, then the set of all vector inside V, which are orthogonal to any other vector in W, will be called orthogonal complement of W. And we denote it by W perpendicular like that, or by formula, it is a set here. And here is some examples for you. If you consider two space, the coordinate plane like that, and you consider the W is x-axis, you will get that one. The W perpendicular will be the y-axis like that. And the orthogonal complement has the following property. The first one, that is, the orthogonal complement is always a subspace of V. And the second property saying that if we intersect the orthogonal complement to the subspace W, we get only one vector, that is a zero vector. And the last property saying if you take the orthogonal complement twice, then you will go back to the original subspace W. And it is illustrated in the picture here. And you can also imagine that with the case of space. And then we study what we call the direct sum. An will be called the direct sum of two subspace W1, W2 if each vector x inside An can be written uniquely as a sum of a vector W1 inside here and W2 inside there. That is, x it can be written like W1 plus W2, and that kind of written is uniquely. In that case, we use the notation O plus like that. And with that, the orthogonal complement will be satisfy the following. Suppose that W be a subspace of Rn. Then the dimension of W plus dimension of W perpendicular is always n. And also Rn then is a direct sum of W and its orthogonal complement. And the last property is already told in the previous slide. That is, if you take double orthogonal complement, we going back to the original subspace W. We define already the orthogonal projection of a vector onto a subspace. But in case the subspace is given with an autonomous basis, the projection of any vector on that will be given by a formula. That is an explicit formula. It is here. So I write it here for you to see. And finally, once again, I repeat to you that we have a property concerning the distance between a vector and its orthogonal projection on a subspace. That is, if we consider a vector V and its projection on a subspace W, then the distance from V to its orthogonal projection is always less than the distance from V to any other vector inside the subspace. Oh, that is, it is written here. It means that you can say that by words, by phrase, that is, among all the vector in the subspace W, the vector, the projection of V on W is closest vector to V. So that is on what we studied last week. Now we continue from that point. We continue from here. So here is what I have just told you. It means that the orthogonal projection of V on subspace W is the best approximation to V from the subspace W. Means orthogonal projection of V on W is closest to V amongst all the vector of the subspace W. Or if you look at the picture, once again, I take the picture, the distance from V to its projection is always less than the distance from V to any other vector W here. That It's very easy to imagine if we look at the picture. Here is something I write it for you to read. Now I turn into what we studied already. That is a 4 fundamental subspace of a matrix. Suppose that A is an m by n matrix. Then you know that we define already 4 fundamental subspace of A. The first one is a column space A. That is a subspace of Rm. And also we have a left known space of A. Is again a subspace of Rm. On the other hand, I mean on the right hand side here, we have a row space of A. It is a subspace of Rn. And also known space of A is again subspace of Rn. I repeat for you that the row space of A is exactly the column space of A transpose. Then we have the following observation. In Rm, column space of A and left known space of A, they are orthogonal and complement of each other. Means if you take the column space of A and you find the orthogonal and complement, it is exactly the left known space of A. And if you find the orthogonal complement of left known space of A, it is exactly the column space of A. The same thing happened with the row space of A and the known space of A is here. If we take the row space complement orthogonal and complement of row space of A, it is exactly the known space of A and vice versa here. More than that, you have the Rm, because of that thing. The Rm is direct sum of the column space of A and known space, left known space of A. And here again, the column space of A and known space and orthogonal complement of known space of A, and so on. And we have things like that. So that is the relation between the 4 fundamental subspace of matrix. We need only to remember only one thing here, and you can imply on the other relation. And here is some example for you. Suppose that you are required to find the 4 fundamental subspace of the matrix A. A is given here, is already in the reduced row echelon form already. You see that you need to find 4 fundamental subspace. The first one, the column space. We have the first column and the last column containing the leading one, so it makes the basis for the column space of A. It is here. The first column and the last column is a basis for the column space of A. And for the row space of A, because that is already in the real reduced row echelon form, so the first and the second row they are non-zero row, so that make a basis for the row space of A or the column space of A transpose. So what is the known space of A? I will not repeat to you how you can solve it, but the known space of A is solution space of the homogeneous system of equation given by the matrix A. And in this case, you can find that the known space of A has a basis consisting of only one vector minus 2, 1, 0. And last, we need to find the left known space of A. And here, once again, left known space of A is exactly the solution set of homogeneous system of linear equation given by the matrix A transpose. And we will find it that it has a basis consisting of 2 vectors like that one. So now we have already 4 fundamental subspace, and you can do by yourself at home. You can verify anything here. You can verify that the orthogonal complement of column space of A equal that. You can verify it by using the definition, and also you can verify on other thing here. So I leave it for you to try by yourself at home. Now I change to something else. That is some more exercise, some more examples. Suppose that we are given two vectors W1 and W2 with the coordinate like that. And suppose that the W is a subspace spanned by that one, by two vectors. And it is a subspace of R4. The first one, you are required to find a basis for W. And the second one, you need to find a basis for the orthogonal complement of W. How you can do it? The first one, the first exercise is very easy. You write the two vectors in the columns. The first column is the second column here. And if you apply the Gauss-Jordan elimination, you get the reduced row echelon form like that. And the first column and the second column here containing the leading one. So it makes a basis for column space of the matrix A. It means that W1 and W2 makes a basis for column space of A. That is, W equals the column space of A, and it has a basis consisting of two vectors like that. That is a basis. Next one, you need to find the orthogonal complement of that. And we know that in the previous slide, in the previous analysis, we know that the orthogonal complement of the column space is a left known space of A. In order to find the left known space of A, first we take transpose of A to be that, and with that we can find the solution set. Solution set is here. It has a basis consisting of two vectors 1 and 2 is here. 1 and 2. So that is W perpendicular or the orthogonal complement of W. That is the way you can do the exercise like that. And you can verify that the dimension of W plus dimension of W perpendicular equals 4. And R4 is direct sum of W and W perpendicular. That you can verify from the definition. Now we go to the problem of the least square problem. It is as follows. Suppose that we are given a system of linear equations AX equal B. A is an M by N matrix. X is a column N by 1 and M is a column M by 1. When the system is consistent, means it has at least one solution. We can use Gaussian or Gauss-Jordan elimination to find the solution. We can find any solution. But in the case the system is inconsistent, it means that we cannot, there is no solution for the system. What do you want to do? We want to find what we call the best possible solution of the system. It means that we need to find a column X so that AX is very close to B, or we can say that AX is as close to B as possible. AX càng gần B thì càng tốt. So it means that we need the difference between AX and B is smallest possible. How we can do it? Here is some example, some explanation. AX equal B is an M linear equation in N variable. And the least square problem means we need to find a vector I denoted by X hat in I, so that X hat minimize the distance between AX minus B. And how we can do it? If we can find such X hat, we will call it a least square solution of the system AX equal B. Again, we explain it. A is an M by N matrix. X is a vector inside Rn, or it's a columns. Then if we multiply A by X, we always get a vector inside column space of A. And we know already that column space of A is always a subspace of Rm. Yes. Subspace of Rm. And because the system is inconsistent, so we know already that B does not belong to the column space of A. That we know already from the many previous lecture. AX equal B is consistent if and only if B belong to the column space. But here is inconsistent, so B does not belong to the column space. Okay, then we need to find a vector X hat inside Rn, so that X hat is closest to B. So which one? AX hat is in the column space of A, and in the column space of A, the vector which is closest to B is orthogonal projection of B onto column space of A. So it is here. I explain it to you again. Then what we need to find? We need to find so that AX hat equals orthogonal projection of B on the column space of. And once again, in order to find that, we use some property. Property saying that the B minus its projection is always orthogonal to the column space of A. And because of that, it means that B minus AX hat belongs to the orthogonal complement of column space of A. But however, we know in previous slide, we know that the orthogonal complement of column space of A is left non-space of A. So it means that B minus AX hat belong to the left non-space of A. Belong to left non-space of A means that B minus AX hat is solution of the system of a linear equation with the matrix A transpose, or AT multiplied by B minus AX hat equals 0. But from here, if we multiply them together, we express that you get AT multiplied by B minus AT multiplied by A multiplied by X hat equals 0. Or if you move that part on the right hand side, you get that one. AT X hat equal AT by B. Now you can see AT multiplied by B, we get a column. AT multiplied by A, we get a matrix. So once again, we get here is a system of linear equation. That system has named normal system associated with AX equal B. So we summarize anything here by the following. First, we are given a system AX equal B, and we know already that the system is inconsistent. So the problem of finding the least square solution means we need to find X hat that is we need to find x hat satisfying that system of linear equation. So we need to find x hat satisfy the associative normal system here. And here is some examples for you. We are given a system AX equal B with A to be that matrix, B to be that one. And we know already that the system is inconsistent. Then we apply on what we explained in the previous slide. First we need to find what is AT multiplied by A. We get that matrix. AT multiplied by B, we get that column. Then the associative normal system is like that. Now AT, A to be that, we substitute it here. AT, B to be that, we put it here. So now the associative normal system becomes that one. And from that, you can solve to find that x hat to be that one. X hat to be the vector like that. But however, you know that the projection of B on the column space of A equal A multiplied by X. So in case you want to find the orthogonal projection of B on the column space of A, you can apply that. You find already X hat to be that one. So you know already what is A. So you multiply A by X hat, you get that one. So that vector is exactly the orthogonal projection of vector B on the column space of A. That is on what we study in the lecture number 5, and we begin right now with the lecture number 6. Now we begin right here. The lecture number 6, we deal with what we call the linear transformation. So first, suppose that we are given two vector space V and W, and we consider a function or mapping T from V into W. So what is a function? What is a mapping? It is a correspond to set each vector inside V into a vector inside W. V which has a name domain of T, and W has a name codomain of T. Or you can see it in the picture like here. The domain is the blue one here, and the codomain is a big purple round here, and the small round here has a name range. We are going to define it in the next slide. And here are some name or some terminology for this chapter. The image of V under T, ảnh của V dưới ánh xạ T. Suppose that we are given T already, and V is a vector inside V, W is a vector inside W. So that T of V equal W. It means that T sends the map T sends the vector V of V to the vector W of W here. Then the W here, the small W here, will be called the image of V under T. The image of V under T. And then now the notion of the range. The range of T, that is a set of all image of vector inside V. Because V, we have so many vectors, so we send any vector inside W, and we consider all the image inside V, inside the W, then it will have the name, the range of T. And there is one more name, that is a pre-image of W. The set of V on vector V inside V, so that T of V equal W, then the set will be called the pre-image of W, the pre-image. So you can imagine that one vector inside W can have many different vector inside V, which send to W. So then the pre-image of one vector in W can have many elements. And here is some example. Now we consider a function going from R2 into R2. The function is given by the formula like that. T of a vector V with two coordinates V1, V2 is given by that. Then you are required first to find the image of V. If V has a coordinate -1 and 2. And the second one, you need to find the pre-image of W with W equal -1 and 11. The first one is very easy. To find T of V, you need only to substitute the coordinate of V into the formula here. You get -3 and 3. But in order to find the pre-image of W, you need to solve a system of linear equation. And it is here. If T of V equal W to be that, then you have that thing. It means that the first one equal -1 and the second coordinate equal 11. Means you have the system of two linear equations. And to solve the system, you get only one solution, C4. In that case, we say the pre-image of W1 W equal -1 and 11 is C4. We have only one element to be the pre-image of W. Now, we are going to define what we call the linear transformation. And usually we abbreviate it by NT. Suppose that V and W are two vector spaces. T from V to W is a mapping from V to W. We call it a linear transformation if it satisfies two properties, very easy to remember. The first one saying T of U plus V equal T U plus TV. And the second one saying T of C time of U equal C time of T U. In here, C is any number, and in the first equality, we have that equality for any vector U and V inside the domain. And usually people say that a linear transformation preserves on operation for a vector space. And for a vector space, you have two operations, the vector addition and scalar multiplication. So we are going to see it here. The first, that is addition, vector addition here. You see that T of U plus V equal TU plus TV. And on the left-hand side, that is addition in V. But on the right-hand side, that is addition in W. We have two operations on different vector space with the same name, that is vector addition. Similarly, for the scalar multiplication, we have that also. Here you have a scalar multiplication in V, and here is a scalar multiplication in W. So you see, a linear transformation is always preserve the operation of the vector spaces. And in case the domain and codomain coincide each other, means T is a mapping going from V into V. Then usually we call it a linear operator. Just only the name might be a little different from case to case. And the examples here ask you to verify the example, the previous example That is a map T from R2 into R2 given by the formula like that is a linear transformation. So how you can do it? You take U with coordinate like that, V with coordinate like that, and then U plus V will have coordinate U1 plus V1, U2 plus V2. Then T of U plus V will be that one. Now, just a simple calculation, you can regroup them together. You will get that thing plus that thing. And that one is exactly the T of U. And the second term here will be the T of V. So we get T of U plus V equal TU plus TV. The same with scalar multiplication. If you take C time of U, you get the coordinate CU1, CU2. And if you apply the formula for T, you get C time of TU. So you see that T satisfies two axioms for a linear transformation. That is what you need to verify here. But that one is examples for the function which is not a linear transformation. Now we are given fx equal psi of x. I believe that you remember the formula from the trigonometry. The psi of x1 plus x2 is always different from psi of x1 plus psi of x2. And you can verify with x1 equal pi over 2 and x2 equal pi over 3. Or otherwise, you can use the calculator to verify that the left-hand side and the right-hand side are different from each other. So we say that in that case, fx equals psi of x is not a linear transformation. The second one, we consider fx equal x squared, and obviously we have that one. You see. The last examples I want to insist to you, that is, if you consider fx equal x plus 1, then you can verify that. Oh, sorry, sorry, I have to go out for a while now. So please take a short break, and I come back in 10 minutes, please. Okay.
Professor.
Okay,
Okay.
Professor.
Okay. Okay. I'm sorry for that. The next one will be the identity transformation. Yes, please. Somebody want to ask something? Okay, the next one will be the identity transformation. That is, a mapping T from V into V itself any vector V in itself. Nothing changed, V into V. And it is very easy for you to verify that both mapping here satisfy on two axioms for a linear transformation. So because of that, they are linear transformation, but they are very special. Now I am going to show you some property for a linear transformation. Suppose that T from V to W is a linear transformation, and U and V are two vectors of a vector space V of the domain. Then the first property saying that T of zero vector inside domain equals always the zero vector of the codomain. The second property saying that T of minus V equals minus of T V. And T of V minus T of the difference between U and V equals the difference between T U and T V. The last property is the most important thing. That is, if V is a linear combination of the vector V1, V2, Vn, then TV will be the same linear combination of TV1, TV2, Tvn with the same coefficient C1, C2 up to Cn. Is here. That is a very important thing, very useful thing. Here you can see it's an example here. Suppose that we are given a linear transformation T from R3 into R3. And we know already that T of 100 equals that, T of 010 to be that, and T of 001 to be that. So we know already that C vector E, E1, E2 is C. Here, E1, E2 is C. Is standard basis for the space R3. Then, if we are required to find T of the vector with coordinate 2C minus 2, it's very easy. You write down the 2C minus 2 as a linear combination of C vector E1, E2, EC. It is here. Then T of the vector, that vector equals that linear combination of the same coefficient 2C and minus 2. So we get that one. So it is very, very easy to do. The next one, the next example is very important thing because it will give us a general picture of a linear transformation. Now we consider a function T from R2 into R3 given by the formula like that. T of V equal A multiplied by V, where A is a matrix like that, and V is written in the column matrix like that one. Then you are required to find the T of V with the V is coordinate 2 minus 1. And then the second one, most important thing, it requires you to show that T defined like that is a linear transformation from R2 into R3. So the first one is very easy, nothing to do with that. You need only to do the matrix multiplication here. You get 6, 3, 0. And for the second one, oh, okay, before that, you can verify by that. Here is a vector inside R2, and here is a vector inside R3. That is exactly a map going from R2 into R3. Then we can say that T of that equals 6, 3, 0. The next one, you need to verify two property of a linear transformation. It is here, T of U plus V equal A multiplied by U plus V. But however, you know that the matrix multiplication satisfying that property. So here you get TU plus TV. And the same thing happened with the scalar multiplication. So we have T of CU equals C times of TU. That two axioms are satisfied So we can say that T given like that is a linear transformation from R2 into R3. We generalize it by consider a map T from Rn into Rn by multiply with a matrix M by N matrix A. Here you see A to be M by N matrix here. And if we multiply that with a column matrix here, you get a column matrix Z. And you see here is a vector inside Rn and here is a vector inside Rn. And we, like in the previous slide, you can verify that the mapping defined like that is a linear transformation from Rn into Rn. It satisfies both axioms in the definition of a linear transformation. And here I write it once again, T from Rn into Rn by the formula like T of V equal A multiplied by V. I want to show you some examples. It is very, if you look at that, first, it seems somehow strange, but however, it is what you know already. It is very familiar to you. Now we consider a map T from R2 into R2, and it is given by the matrix A with a cosine of zeta minus sine of zeta, cosine of zeta. Zeta is a fixed angle. And I claim that that one is a rotation, là phép quay. So I show you. Suppose that V is given with the coordinate X and Y. We can rewrite it like A cosine alpha and A sine alpha. And that is what we call the polar coordinate, tọa độ cực. And what is A? A here is the length of the vector. And what is the alpha? Alpha is the angle from the positive X axis. And we count it counterclockwise to the vector V. Counterclockwise in Vietnamese, ngược chiều kim đồng hồ. So here, look at the picture here. Let the point, the vector V is here with the coordinate X and Y. So what is A? A is the length from here to there. That is the length. And the angle alpha is here. The angle from the positive X axis to the vector V. So alpha is here. And it is very easy for you to find that X here is exactly A cosine alpha. And the Y is A multiplied by sine alpha. So that is the coordinate X, Y. And if we apply the map T of V equal A multiplied by V, we get that one. But now we replace X by A cosine alpha and Y by A sine alpha. You get that one. And I believe that you remember the formula from the trigonometry that the first line will be A cosine of zeta plus alpha, and the second line here is A sine of zeta plus alpha. So you see that now A is the length of T of V, and zeta plus alpha is the angle from the positive X axis counterclockwise to the vector T of V. So with that, you see TV is a vector we obtain from the rotate the vector V counterclockwise by the angle zeta. Vector TV nhận được từ vector V bằng cách là chúng ta quay nó đi một góc zeta, giống như cái hình ở trang trước. Here. From xy here you get T of xy here. We rotate it by an angle zeta here. So that is that mapping is given with the matrix A like that. The next example show you, if you consider a linear transformation T from RC into R3 by a matrix A like that, then if you verify by the coordinate, it is nothing but the projection on the xy plane. It sends x, y, z to the point with the coordinate x, y, 0. So that is the example here. I give you some more examples here. The linear transformation from m by n into m n by n. It means that we send a matrix A to its transpose. Then the sign of that will be changed. Then that one again is a linear transformation. Why is that? Because we need only to verify two axioms in the definition of a linear transformation. And that is very easy to verify because we know already the property of transpose of a matrix. So I leave it for you to read the slide by yourself. Next, I want to show you the notion, the canon and the range of a linear transformation. Now, suppose that T from V to W is a linear transformation. Then the set of on vector V inside the domain satisfying that T of V equals 0 will be called the canon of T, and it is denoted by that canon of T. Or by formula you have the canon of T is a set of on vector V so that T V equals 0. Then if you consider the case when T is a transpose map from MC by 2 into M2 by 3, the canon will be 0 matrix, only 1. And we consider two special linear transformation. The first one is zero transformation. You remember that by definition, T from V to W, sending on the vector V in the domain into the 0 vector of W. It means that the canon of T is a whole domain here. It means that on the vector V of the domain belongs to the canon of T. That is the first example. The second example is the identity transformation T from V to V itself. Because T of V equals V like that, then when here is a 0 vector and here must be 0 vector. In that case, the canon of T is only one vector, that is a 0 vector of the domain. Okay. So we have two special cases. Now we look at the non-Tbn example. Now we consider once again the projection of the C space onto XY plane. It is given by the map like that. XYZ is sent to XY0. Then obviously, very easy to see that. Then the canon of T will be 0, 0, Z. It means that when you have 0, 0, Z here, it is mapped to 0, 0, and 0 here. And it is a 0 vector inside R3. So if you look at the picture here, what is the canon of T? The canon of T is exactly the vertical axis here. That is OZ axis here. So that is another example for you. And now, if you look again at the case when Tx is given by a matrix, once again, I going back to the previous example. Suppose that Tx equals Ax with A to be the matrix like that, and you are required to find the canon of T. you are seeing that now you are return to solving a system of linear equation. Okay, by definition, Canon of T equals on x1, x2, x3, so that equals 0. So it means that T of x equals 0. Now we write down here, if A multiplied by x1, x2, x3 equals 0, or that equivalent to write it in system of linear equation like that. In order to find the Canon of T, you need to find the solution of that homogeneous system of linear equation. And solving it, you get the solution like that. So the Canon of T is the set T time of 1 minus 11. Sorry, 1 minus 1 and 1. Which T is a real number. So we can say that Canon of T is spanned by the vector, by one vector, that is this vector. So from the previous example, we see that the Canon of a linear transformation T is a linear transformation from V to W, and its Canon is always a subspace of the domain. It's lying inside V, and it's always a subspace of the domain. It is explained here in the slide on the Moodle, so you need to read it by yourself. And because of that, sometimes we call T is the non-space of T. The Canon can be called the non-space of T. Once again, we look at a previous example. T from R5 into R4 with that Tx equal A, x, with A is that matrix. You are required to find the basis for the Canon of T. Then obviously you see that is similar to you need to solve to find the solution space of a homogeneous system of linear equation. And you apply Gauss-Jordan elimination to solve it. You change it into row echelon form like that, and the first, the second, and the third, and the fourth column containing the leading one means the third and the fifth will be the variables. It will be free variable, and then our solution will be that the third and the fifth will be free solution, and on the other solution, other variable can be solved according to S and T. And finally, our solution will be S time of that vector plus T time of this vector. That means this vector and that vector makes a basis for the Canon of T, or the basis for the solution set of the system of linear equation. So that is in case the linear transformation T from Rn into Rn given by a matrix like that, Tx equal A time of x, then the Canon of T equal the solution space of the homogeneous system of linear equation Ax equal 0. And we write it in the formula like that. Now we go to another thing. That is the notion, the range of a linear transformation T. Suppose that T from V to W, V to W is a linear transformation. Then the set of on vector inside W, which is an image of some vector inside V, will be called the range of T. The definition, we define it already from the first or the second slide of the lecture number 6. Then by formula we have the range of T equal that equal on the W inside here, so that W equal T of V for some V inside the domain. Then again, we have the range of T is always lie in the codomain W. And our observation says that the range of a linear transformation T is a subspace of the codomain. It is a subspace of the codomain. And again, it is explained in the slide. You need to read it by yourself. And by the picture, it is illustrated in the picture like here. The domain is a blue one. The codomain is a big open around here. And the Canon is a small one here. It is a subspace of the domain. And the range is a small purpose around here. It is contained in the codomain. And it is a subspace of the codomain. And we have another observation saying that in case the linear transformation T from Rn into Rm given by a matrix A, the range of T then will be the column space of A. That is, the range of T equals column space of A. So because of that, suppose that if you are given a linear transformation T from R5 into R4 with the formula Tx equal Ax, and A is a matrix like that, and if you are required to find a basis for the range of T, it means that you need to find a basis for the column space of A. To do that, very easy. You transform it A into row echelon form. Then the columns containing the leading one will be a basis for the matrix B. Then the corresponding column of A will be the basis for column space of A. So we get C1, C2, and C4 will be a basis for column space of A. And it is obviously it is a basis for the range of T. Now next, that is some name. The range of a linear transformation T from V to W. The range of T will be defined to be the dimension of the range of T. And we can also define the nullity of a linear transformation T from V to W. We define it to be the dimension of the Canon. So for a linear transformation T from V to W, we have the Canon. The dimension of the Canon will be the nullity. And we have the range. The dimension of the range will be the rank of T. And in case T is given by a matrix like that, you get back again what we studied already. Now in that case, the rank of T is exactly the rank of the matrix A. And the nullity of T is exactly the nullity of A. And because of that, we see, once again, we have the following relation between the rank of T and the nullity of T. Suppose that T from V to W is a linear transformation from an n-dimensional vector space V to any other vector space W. Then we have rank of T plus nullity of T equal n. Or otherwise, if you write down what is the rank, what is the nullity, we get that thing. And once again, it is explained in the slide. I leave it for you to read. And here is some example. If you are given a linear transformation T like that on the screen, and you are required to find the rank and the nullity of T. So the rank of T is the rank of A. And because that is already in the row echelon form, so you see the two knowns A has two non-zero row, then the rank of A equal 2. And because of that, the nullity of T equals 3 minus 2 equal 1. So it is very easy. Next, if you are given T from R5 into R7 is a linear transformation. And here some examples A, B, C require you to find the dimension of Canon, the dimension of the range, and something like that. No. To find the dimension of the Canon if we know already the dimension of the range, and that is something like that. And B and C again, they always use the relation between the rank and the nullity of T. So here it is explained in here. If the with the given exercise, given example, the dimension of the domain is 5 always. Is that? Then, if we know already the range is 2, then the nullity will be n minus 2 is 3. That is for the first exercise. For the second one, again, the rank of T equal n minus nullity. And in that case, nullity of T is 4, so the rank of T equal 1. And you can do by yourself to solve the exercise number C here. Next, I introduce you the notion of one-to-one function or mapping. The one-to-one in Vietnamese we say đơn ảnh, function ánh xạ, one-to-one function ánh xạ đơn or đơn ảnh. So here is a definition. A function T from V to W will be called one-to-one if the pre-image of every W in the range will consist of only a single vector. Or if you want to have some formula to do the exercise, that is T is one-to-one if and only if for U and V in the domain. If we have TU equal TV, it implies that U must coincide to V. And here is the illustration for you to imagine. The map on the left-hand side is one-to-one because the pre-image of each vector here consists of only one single vector on the domain. But the map on the right-hand side is not a one-to-one. Why is that? Because you can find that vector. It has a pre-image consisting of two different vectors inside the domain. So that one is not one-to-one. That one is one-to-one. And by definition, you can see it here. We have another notion that is onto mapping. Onto mapping. Onto in Vietnamese is lên. Onto mapping, ánh xạ lên or toàn ảnh. Okay, now name is only the name. You can imagine, you can see the definition here. A function T from V to W will be set to be onto if any W in the codomain will has at least a pre-image in the domain. That is, you can imagine very easy. In that case, the range and the codomain must coincide, must equal each other. So T is onto W when W equal to the range of T. That is an explanation for that. So events one-to-one and onto is a very interesting property of the mapping. But however, we need to know how we can verify a map to be one-to-one and to be onto. And in case T is a linear translation, it is very easy to verify if T is one-to-one or not. So here it is. If T from V to W is a linear translation, then T is one-to-one if and only if its Canon consists of only one vector. It is a zero vector. That is, we have a criterion to verify if a linear translation to be one-to-one or not. And it is explained in the slide. And here is some examples. The example for some linear transformation which is one-to-one and someone is some other is not one-to-one. And the first one I want to show you, that is transpose map. The map sending a matrix A to its transpose. That one is one-to-one. Why is that? Because the Canon in the previous slide we show that its canons consists of only m by 1 0 matrix. So m by n matrix having on entry to be 0. So that is one-to-one. And the second one I want to show you, that is zero translation T from RC into RC. That one is not one-to-one. Why is that? Because the T sending on vector in RC into the zero vector in here. So the Canon of T equal on RC. The Canon is on the domain here. So it cannot be one-to-one. So how we can verify a linear transformation to be an onto mapping? Here is some criterion for you to verify. We know already that a mapping is onto if and only if the domain and the range equals each other. And now in case L, in case T is a linear transformation and the domain is a finite dimensional vector space, then T is onto if and only if the range of T equals the dimension of the codomain. And because the range must equals W, and then the range is the dimension of the range equals the dimension of the codomain. So that is one criterion for you to verify if a linear transformation T is onto or not. So you know we have two different notions: one-to-one mapping and onto mapping. That is quite different. But however, we have one cases. In that cases, one-to-one and onto are the same. It is here. Suppose that V and W, they are vector space of the same dimension n. V and W, domain and codomain, are vector space of the same dimension n. And suppose that T from V to W is a linear transformation, then T is one-to-one if and only if it is onto. If it is one-to-one, then we know that it is onto, and vice versa. If T is onto, we know that it is one-to-one. That is only in the case V and W are of the same dimension. And again, it is explained in the slide, so I will not go into the explanation here. And now we consider the examples. We consider the T from Rn into Rm given by T, given by a matrix A like that. You are required to find the nullity, to find the rank of T, and you are required to determine whether T is one-to-one. Sorry, I have some phone I need to answer right now. So please wait for me a little. Sorry, so let me continue. Now, the example here is you are given a mapping defined by a matrix A like that, and you are required to find the nullity, the rank of the mapping T, and then you need to determine if T is one-to-one onto, or if it is not onto, not one-to-one. And here the example is a very long one. You have 4 cases A in the 4 cases a matrix like that. Then the answer for you is in a table like that. The first column here is the dimension of the domain is very easy. Here is 3, 2, 3, and 3. That is the dimension of the domain. And the rank of T, you just only to count how many non-zero rows here. So it is very easy. For the nullity, we use the notion, the relation between the rank and the nullity and the dimension of the domain. You can get anything here. So the nullity is very easy to find here. Then once again, you look at the criterion before to see if the map is a one-to-one or not, and it is onto or not. So I suppose that you can verify it by yourself. So that by looking in the previous slide. So I will not stop it here. I explain to you that the notion, the isomorphism, a linear transformation T from V to W, which is one-to-one and onto at the same time, will be called an isomorphism. Một ánh xạ tuyến tính từ không gian V vào V kép và là ánh xạ là đơn ánh và ánh xạ toàn ánh hay ánh xạ lên đồng thời sẽ được gọi là một đặc cấu isomorphisms. In Vietnamese đặc cấu. Moreover, if two vector space V and W, and so that we can find an isomorphism from V to W, then two vector space V and W will be called isomorphic to each other. Nếu có một đẳng cấu giữa V và V kép thì chúng ta sẽ nói hai không gian V và V kép đẳng cấu với nhau. V and W are isomorphic to each other. Then, in order to verify if something is isomorphic to each other, we know we have the following things. Two finite dimensional vector space V and W will be isomorphic to each other if and only if they are of the same dimension. Yeah. And once again, it is explained in the slide, and you need to read it at home. And the homework for you. Suppose that you are given three mapping here. The first one, A, has name projection. The second one has named diagonal, and the last one has named the reflection. In Vietnamese, the first one là phép chiếu, the second one là ánh xạ đường chéo, the last one là phép phản xạ hay là phép đối xứng. So the first one, you need to verify that all three mapping are linear transformation. The second one, you need to verify which one is one-to-one, which one is onto, and which one is isomorphisms. So that is your homework of today. So I suppose that today we will stop here, and we see each other next week. So if you have some question, please ask me now.
Goodbye, teacher.
Oh, you say goodbye. You don't want to ask anything?
No, sir. Thank you, sir.
So how about the
when is the midterm?
Yeah, okay. That is always. About the midterm, I can tell you that we cannot have it this weekend. Why is that? Because as I told you already, the IT service as a USTH, I mean the service of công nghệ thông tin in the USTH, they don't have enough human resource to upload the exercise on the Moodle for you to do the exams by this weekend. So we do it next weekend, I promise. But however, you are going to have a test midterm exams, sẽ thử thi midterm by this weekend. The exact date and time will be announced on the Moodle. So please follow that on the Moodle. Okay. Is it clear for you?
Okay.
Yes, thank you.
Excuse me, but
thi thử thì có nhất thiết là phải đúng theo thời gian mà người ta bảo không, hay là mình thi lúc nào cũng được?
So you should follow the same way like an official midterm exam. Means you need to follow exact timing for the midterm.
The next weekend there are some people have the military training, so
okay, so we will choose some the correct time, so the suitable time for all students can participate in the midterm exams.
So yeah, so thank you.
Thầy ơi, mình sẽ thi tất cả các lecture.
Chắc là không phải tất cả, nếu mình thi tất cả thì đến final còn cái quái gì để thi nữa đâu.
Thế thi từ lecture 1 đến lecture 5.
4.
Cái đấy sẽ được thông báo kỹ cho các bạn, không sao đâu. Sẽ thông báo sớm thôi, xem là thi từ chỗ nào đến chỗ nào nhé. Thông báo trước khi thi thử, trước khi làm cái bài test. Cần có một cái bài test để cho các bạn quen thuộc với cái việc là thi ở trên Moodle sẽ như thế nào. Any more question?
No. Vậy thì thi thì có bắt buộc phải tham gia không ạ?
Tùy
Thì
các bạn có thể không tham gia cũng được, kể cả midterm các bạn cũng có thể không tham gia cũng được mà. Đùa đấy, không có gì đâu. Tất nhiên là các bạn nên tham gia. Các bạn nên tham gia cho nó vậy.
Em ơi, thầy bao giờ thi thử ạ?
Tôi vừa mới nói xong, thi thử sẽ xảy ra vào cuối tuần này, nhưng ngày giờ cụ thể sẽ được thông báo ở trên Moodle, cho nên các bạn chịu khó theo dõi cái announcement ở trên Moodle nhé. Chắc là ngày mai ngày kia thì sẽ thông báo thôi.
Thầy ơi, thi thử có kết quả và đáp án giải các thứ không?
Các bạn sẽ có được mọi thứ ở trên đấy. Nhưng mà có cái gì mà đáp án với ấy đâu, thì online thì các bạn biết rồi. Tóm lại là các bạn sẽ nhìn ở trên đấy thì sẽ nhìn trên đấy thì các bạn sẽ biết cách thi là như thế nào.
Kiểu là biết con nào đúng con nào sai ạ?
Tất nhiên.
Vâng.
So if no more questions, so I would like to say goodbye to you and see you next week.
See you.
Bye, professor.
Bye, professor.
Bye.
Bye, professor.
Bye, teacher.
Goodbye, professor.